Hello everyone, my name is Pritha Paul. I will be presenting work that I have been doing with Roy Martins and Chris Clarkson. This talk will focus on the parity-odd component of the observed trispectrum. So far, the power spectrum has been a key observable in probing the large-scale structure of the universe. We have been very fortunate to have rapid advancement in the large-scale structure surveys, with lots of current and upcoming surveys such as Euclid, DESI, and SKAO. From this plot of the power spectrum, we can see that there are lots of constraints on the equality scales, but fewer as we go towards smaller values of K or larger scales. However, with the upcoming surveys, we plan to get data on the larger scales, so it is increasingly important that we have a robust theoretical foundation that takes into account these effects that dominate at these scales. Alongside that, we can also look at the statistics, which is beyond the power spectrum. The next higher order statistic would be the bispectrum. In real space, it is known as the 3-point correlation function, and now we count triplets of galaxies. We can go a step further and calculate the 4-point correlation function. The 4-point correlation function probes tetrahedral shapes formed by 4 galaxies, with its Fourier counterpart being the trispectrum. So why do we need higher order statistics? One of the reasons is to probe primordial non-Gaussianity. If our late universe was fully Gaussian, all the information would have been contained in the power spectrum or the 2-point correlation function. But if it is not, then there is information that leaks into the bispectrum and the trispectrum and so on. We can also use it for breaking parameter degeneracies and to get better cosmological constraints. On the plot here on the left, we can see that combining the power spectrum and bispectrum gives much tighter constraints on the parameters than just the power spectrum. Including trispectrum in the analysis could also potentially give much tighter constraints. Finally, we can also use higher order statistics to probe parity violation. Power spectrum and bispectrum is not sensitive to parity. When they undergo a parity transformation, that simply results in a rotation. However, the trispectrum is the lowest order statistic that is sensitive to this parity transformation. When we consider the trispectrum, we are looking at tetrahedral shapes formed by galaxies. The easiest way to picture it is when the trispectrum or the 4-point function undergoes a parity transformation, the tetrahedral is the lowest order geometric shape that cannot be superimposed on its mirror image. As a result, it is sensitive to parity transformation. This is not true for the case of the power spectrum and the bispectrum, as they are either a line or a triangle, so that can be superimposed on its mirror image. Recently, several groups have looked at this parity violation that arises in the 4-point function. Hu et al. Have looked at the BOSS catalog, where they have focused on 2 populations of galaxies, which was the LOES and the C mass, and they found a 3.1 sigma evidence and a 7.1 sigma evidence for a non-zero parity-odd 4-point correlation function. They were also probing scales of 79 megaparsecs, which is roughly near the equality scales. So now it is becoming increasingly important to look at the 4-point function or the trispectrum in details. My talk will focus on the observed trispectrum in redshift space. When we observe, we don't observe the real density fluctuations. Instead, we observe in redshift space, which induces lots of distortions which are accompanied to these real fluctuations. The first approximation was given by Kaiser, and they are known as the standard redshift space distortions. They are symmetric along our line of sight. However, there are effects which are suppressed by h over k compared to these standard distortions, where h is the conformal Hubble rate. These distortions are usually induced by peculiar velocity and gravitational redshift, which breaks symmetry along our line of sight. The ellipses are distorted into asymmetric shapes instead of symmetric shapes, which is the case of the standard Kaiser RSD. I will come back to these redshift space distortions a bit later on in my talk. However, now we will set up our trispectrum with a line of sight. We have the four k wave vectors, k1, k2, k3, k4. They close to form a quadrilateral. We also have the line of sight n. Capital theta and capital phi represents the configuration angles, so changing these angles changes how your quadrilateral will look like. We also have small theta and small phi, which represent the viewing angles. We also have psi, which represents the folding angle. So this is the angle between the two triangles in the quadrilateral, which is broken by the vector d. Alongside that, we have now also set up the theoretical setup for the trispectrum. We can construct the trispectrum by cross-correlating 4 observed galaxy number density fluctuations. This ends up giving the trispectrum and the Dirac delta function. The Dirac delta function imposes the constraint that the quadrilateral closes on itself. We also have to expand the density field to third order. So this includes the second order density field and the third order density field. At tree level, the terms that contribute to the trispectrum are the second and the third order terms. So this includes a combination of 1113 with 4 cyclic permutations and 1122 with 6 cyclic permutations. The permutations are in K. So for the first line, it is symmetric in K1, K2, and K3, and the permutations occur in K4. We can also break the density field down into 2 parts, one which consists only of the standard RSD contributions, and the other one is the GR contribution, so we take into account the relativistic effects that come into play at large scales. So delta GR is suppressed by H over K compared to delta Newtonian, and these effects mainly come into play for very small values of Ks, which means that once we go to very large scales. Here I have given the first order contributions. These include the standard Kaiser terms. The first term is the true galaxy fluctuation coupled with a galaxy bias B. It also includes the term which is the radial derivative of the peculiar velocity. However, it is interesting to note that all these terms are symmetric along our line of sight. Mathematically, we can see that all of these terms have even powers of n. As a result, when we do a parity transformation, so when n goes to minus n, these terms don't change sign. In contrast, the first order relativistic contribution only contains the term with v parallel. As we can see mathematically, the term v parallel only has odd power of n. This means that when n goes to negative n, this is going to change sign and give rise to a parity odd contribution. These effects are not symmetric along your line of sight, and it gives rise to asymmetric shapes. We can also see that there are terms in this relativistic contribution such as S and F evo. S stands for the magnification bias and F evo stands for the evolution bias. Both of them are dependent on the survey that we use to calculate our observed trispectrum. They also contribute to the parity odd contribution, and changing the galaxy survey changes these evolution and magnification biases. For the trispectrum, we also need to consider second order contributions. For the second order contribution, we also have the Newtonian terms and the relativistic terms. The Newtonian terms now include the second order density fluctuation. It also has the second order radial derivative of the peculiar velocity. There are some more coupling terms between v parallel and delta g. For the relativistic contribution, we have the second order peculiar velocity contribution, and we also have the magnification and evolution biases there as coefficients as well. Mathematically, the idea remains still the same. For the Newtonian contributions, all the terms in there are even powers of n. This means that when n goes to negative n, none of the terms change sign. For the relativistic contribution, all these terms are odd powers of n. As a result, when we do the transformation n going to minus n, this results in a parity odd contribution. For the trispectrum, we also require the third order contribution. For the third order contribution, we now have the third order density fluctuation. We have lots more terms. We have more coupling terms between the peculiar velocity and delta G. However, all the terms are still even powers in n. As a result, we don't expect delta 3n to give us the parity odd contribution. In contrast, moving to the relativistic contribution, we now have the third order peculiar velocity contributions. We also have transverse derivatives. As we can see, there are many more coupling terms in here. However, the idea is still the same in the sense that the relativistic contributions are all odd powers of n. As a result, they give a contribution to the parity odd part of the trispectrum. To note, there are also coupling terms between the peculiar velocity and the time derivative of delta G as well. So now we come to define the odd and even trispectrum. The even trispectrum is defined by Tg plus Tg of k going to negative k, while the odd trispectrum is defined in a very similar way, except instead of having a plus, we have a minus. This means that the T even part isolates all the Newtonian terms, while the T odd part isolates the relativistic effects. Just to note that in the T odd bit, there are also terms which have GR and Newtonian contributions with them together. So there are not just purely relativistic terms, there are also coupling terms between Newtonian and GR. Now we get to the main result of this paper, where we plot the odd and even trispectrum. So in this plot, we have plotted T odd and T even as a function of scale. We note that the T odd contribution is plotted as dotted lines, and T even is plotted as straight lines. The black lines correspond to the Euclid-like survey, and the orange lines correspond to SKA intensity mapping like survey. We have specified the geometry on the top, where the configuration angles are big theta and big phi. The folding angle is psi, and the viewing angles are small theta and small phi. We can see that the even contributions peak roughly at equality scales, just before equality scales, and then they start to go down. However, the odd contributions, they also peak roughly at equality scales, but they take over the even contribution as we go towards larger scales. Even just below equality scales, we can see that they are 10% of the even trispectrum. And as we move towards larger scales, they take over the even contribution. We also see the same trend for both Euclid and SKA, except that there is a difference in amplitude for the odd and even contribution. However, for both the surveys, we see that these contributions or corrections become very important as we go to larger scales. In this figure, we show the ratio of odd to even parity trispectrum. This is for a Euclid-like survey at redshift 1. We fix the quadrilateral and we change the scale and the viewing orientation, which are represented by the angles theta and phi. The regions of orange and red, they both indicate corrections of 10% or more. We can see that most of the plot is orange and red, which indicates that for most of the viewing angles and scale, we have corrections which are 10% or more. We also can see the BAO wiggles at the top of the plot. We also note that the trispectrum consists of second and third order contributions. So when we first constructed the trispectrum, we saw that it consists of terms which are 1, 1, 1, 3, which are referred to as the third order contributions, and 1, 1, 2, 2, which are referred to as the second order contributions. We also did some plots where we varied each of the contributions with different configuration angles and folding angle. Here is a plot of T odd over T even, so the ratio of the odd over even part as a function of one of the configuration angles theta. So as we can see that the third order contribution is dominant over the second order contribution as we go for values of theta being less than 5 pi by 8. We can also see that there are some very interesting cancellations going on because the total ratio T odd over T even, which is represented by the red line, is lesser in amplitude than the individual contributions. For values of theta which are more than 5 pi by 8, these cancellations are significant, while if we look at the other values of theta which are less than 5 pi by 8, these cancellations are lesser in amplitude. We are also going to investigate these in more in an upcoming long paper that should be out on arXiv very soon. We have plotted the same ratio T odd over T even for now the folding angle psi. Just to remind ourselves what the folding angle is, it is the angle between the two triangles that form the quadrilateral. The flattened configuration refers to the angle where psi is equal to pi. We can see that there is lots going on in this graph. The black line is representative of the T1113 contribution. The blue line represents the T1122 contribution, while the red line represents T odd in total. We can see for values of psi being less than pi by 4, there is again significant cancellations that go on between the two contributions. We can also see at values of psi being 0.47 pi and roughly 0.17 pi is where the two contributions cross each other. So they are exactly equal to each other and they change sign. We also have points in the graph where T even is equal to 0. As a result, we can see that it really depends on the folding angle, what kind of contribution you get for the T odd part. We can also see there are very interesting cancellations that happen between the two individual parts, which actually reduces the amplitude of the total odd part in this case as well. This brings me to the conclusions of my talk. We have seen that parity violation in the 4-point correlation function has been detected. We have worked with the trispectrum, which is the Fourier counterpart of the 4-point correlation function. We have seen that scales beyond equality scales, there is 100% correction, and below equality scales, there is still a 10% correction. Previous studies who have looked into this parity violating part have not included this effect. And we think it is important to be aware of this effect so there is no contamination when we are aiming to detect intrinsic parity violation. We are also planning to do a longer paper which explores all these effects which are present in both the second and third order contributions of the trispectrum. This paper will be out on the arXiv very soon. Thank you.